The universe.
Yeah.
It's just so incredibly vast, isn't it?
Yeah.
And mysterious, full of stars, galaxies. Makes you wonder, where did it all actually come from?
It really does.
So let's dive straight into that enormous question today, because here on the Deep Dive, we're going to explore the leading scientific explanation for how our universe began and how it's evolved. That's the Big Bang Theory.
Exactly. We'll look at the really powerful evidence supporting it.
Yeah, and maybe touch on some of the mind-bending questions scientists are still trying to figure out.
Right. And it's crucial to understand what the Big Bang Theory actually says. Basically, it tells us that about 13.8 billion years ago, the entire universe was compressed into this incredibly hot, dense state.
Unimaginably hot and dense.
Exactly. And ever since then, it's been expanding and cooling down. And one really key thing to remember,
What was that?
it wasn't an explosion in empty space. It's space itself expanding.
Yes. That's such an important distinction. Not like a bomb going off. It's the fabric of space itself stretching, carrying everything along with it. And it seems like the scientific community is pretty much agreed on that age, right? Around 13.7, 13.8 billion years. See those numbers from NASA, from CERN?
Yeah, quite consistently. The analysis from, all sorts of different data points gives us really strong agreement on that age estimate.
Okay.
The findings from places like NASA and CERN really point to this broad consensus. There might be tiny uncertainties in the calculations, sure, but that age is a cornerstone of the model. It's backed up by multiple independent lines of evidence.
So this huge idea, how did it even come about? Who were the pioneers who started putting this cosmic puzzle together?
Well, the initial groundwork, you could say, was laid by Georges Lemaitre. He was a Belgian astronomer and actually a Catholic priest, too.
Georges Lemaitre.
Right.
Priest and scientist. That's fascinating.
It is. And back in 1927, he first proposed this idea that the universe originated from a single point, or a primeval atom, as he called it.
Wow. That must have been pretty radical back then.
Oh, definitely. And even a few years before him, in 1922, a Russian physicist, Alexander Friedmann.
Alexander Friedmann, okay.
He'd already worked out some really crucial mathematical equations based on Einstein's general relativity, and his math supported the possibility of a universe that wasn't static, but was actually expanding.
So the theoretical groundwork was there, suggesting expansion mathematically, but what about seeing it? What was the actual proof?
That came in 1929 with the crucial observations made by Edwin Hubble.
Ah, Hubble. Of course.
He showed that distant galaxies are moving away from us, and even more importantly, that their speed, the recessional velocity, is directly proportional to their distance. That's what we now call Hubble's law.
Seeing those galaxies rushing away faster the further out they are, that must have been a real bombshell moment for astronomy.
Absolutely.
But I seem to remember reading his first estimate for the age of the universe was, well, a bit off.
Yes, that's true. Hubble initially underestimated the age quite significantly, but that just reminds us about the iterative nature of science, doesn't it? We learn, we refine our understanding, we gradually get closer to a better picture.
Yeah, science in action. Okay, so we have the theory. We have Hubble's observations as the first big piece of evidence for expansion. Let's get into the real bedrock now, the pillars supporting this whole theory. Redshift is a huge one, right?
Definitely. The redshift we see in the light from distant galaxies is one of the most critical pieces of evidence for the Big Bang.
And redshift means the light is stretched out towards the red end of the spectrum.
Exactly. It indicates those galaxies are moving away from us.
Now, it's important to understand this isn't quite the same as, say, the sound of a siren changing pitch as it passes you. That's the Doppler effect, isn't it?
That's right.
Cosmological redshift is different somehow.
Precisely. The Doppler effect describes wavelength changes due to relative motion through space. Cosmological redshift is actually caused by the expansion of space itself.
Ah, okay.
Imagine drawing waves on a rubber sheet and then stretching the sheet. As the sheet stretches, the waves get longer, right?
Yeah, I can picture that.
It's the same idea. As space expands, the light waves traveling through it get stretched out, causing the redshift we observe.
That's a great analogy. So it's not galaxies flying through space, it's space carrying them away as it expands. And this redshift, like Hubble saw, follows that specific pattern, Hubble's law.
Exactly. Hubble's law of velocity proportional to distance is really powerful support for a uniformly expanding universe. It also lets astronomers kind of rewind that expansion back in time to estimate the age of the universe.
Okay.
And there's another twist here. Observations of distant supernovae have shown that the expansion isn't just happening, it's actually speeding up.
Accelerating. Wow.
Yeah, driven by this mysterious thing we call dark energy.
Dark energy. Okay, that sounds like something we absolutely need to circle back to.
Yeah.
But sticking with the evidence for the Big Bang itself, the cosmic microwave background, the CMB, that's another huge piece, isn't it? Like the afterglow.
You got it. The CMB is essentially the faint leftover heat, the afterglow, from the Big Bang itself, permeating the entire universe. It was discovered, actually by accident, in 1964 by Arno Penzias and Robert Wilson.
Penzias and Wilson. Right, they were working at Bell Labs, weren't they?
Mm-hmm.
Picked up this annoying hiss they couldn't get rid of.
That's the story. And that hiss turned out to be the residual heat from a crucial era about 380,000 years after the Big Bang, called the epoch of recombination.
Recombination. What happened then?
That's when the universe had cooled down enough for protons and electrons to combine and form neutral hydrogen atoms. And that process made the universe transparent to light for the very first time. The CMB is basically that light finally free to travel.
And this CMB light, it has very specific features, like a fingerprint, that match the Big Bang predictions perfectly.
Yes, exactly. The CMB shows an almost perfect blackbody spectrum. Think of it like the characteristic pattern of light emitted by a hot object in this case, the very hot, dense early universe. The fact that the CMB matches this pattern so precisely is really strong evidence for that early, hot, dense state. Plus, incredibly sensitive measurements have found tiny temperature variations in the CMB. They call them anisotropies.
Anisotropies. Tiny differences in temperature across the sky.
That's right. And these slight fluctuations are incredibly important. They were the seeds for the large-scale structures we see today, like galaxies and galaxy clusters.
So those tiny ripples in the afterglow eventually grew, pulled together by gravity, into everything we see now. That's mind-boggling.
It really is. The amazing uniformity of the CMB, combined with these tiny anisotropies, paints a very compelling picture of the early universe.
And there's a theory called inflation that explains why it's so uniform.
Exactly. The theory of inflation posits a period of incredibly rapid expansion in the first tiny fraction of a second. That helps explain this remarkable smoothness over vast distances. And studying those anisotropies helps astronomers figure out the universe's overall geometry and composition.
And the CMB is the oldest light we can possibly see, right? Like looking back almost to the beginning.
It is. It's fossil radiation, limited only by the universe being opaque before recombination. It gives us a direct snapshot of the very early universe.
Just incredible. Okay, so we have redshift showing expansion. The CMB is the afterglow. The third big pillar is the abundance of light elements. How does that support the Big Bang?
Well, the Big Bang Theory makes very precise predictions about the amounts of the lightest elements found in the universe: hydrogen, helium, a little bit of lithium.
Right.
These elements were forged in the first few minutes after the Big Bang through a process called Big Bang nucleosynthesis.
Big Bang nucleosynthesis.
And the observed ratio of hydrogen to helium throughout the cosmos, roughly 3 parts hydrogen to 1 part helium by mass, is a major confirmation of the theory. It matches the predictions beautifully.
So it's like the theory gives us the recipe for the early universe.
Rematch.
And when we look out, the ingredients are there in exactly the predicted proportions.
Exactly. The precise amounts of these light elements are very sensitive to the conditions in the early universe. It's temperature, density, expansion rate. The agreement between what's predicted and what we actually observe is incredibly powerful support for the Big Bang model and those early conditions. Other cosmological models really struggle to explain these observed abundances convincingly.
That is strong support. Okay, let's zoom out a bit. Can we get a sense of the overall timeline? What were the key stages in the universe's evolution according to the Big Bang?
Sure. We can break it down into key epochs, starting from the very, very beginning. First, there's the Planck epoch, the first tiny fraction of a second, less than 1043 seconds. Here, quantum gravity is thought to rule, and our current physics kind of breaks down.
The very edge of known physics.
Right. Then came the inflationary epoch, that period of hyperfast expansion we mentioned, maybe from 1036 to 1032 seconds, crucial for explaining the universe's smoothness.
Okay, inflation.
As it cooled, fundamental particles started forming in the quark epoch, followed by the hadron epoch, where quarks combined into protons and neutrons, then the lepton epoch, where electrons dominated.
So building blocks forming very quickly.
Very quickly. Then came Big Bang nucleosynthesis, lasting a few minutes, where those first Light atomic nuclei, hydrogen, helium, lithium were created.
The recipe we just talked about.
Exactly. For the next 380,000 years or so, during the photon epoch, the universe was this hot, dense plasma of nuclei, electrons, and photons. Light couldn't travel freely.
Right, it was opaque.
Until recombination, around 380,000 years, that's when neutral atoms formed, the universe became transparent, and the CMB light was released.
And after that?
That ushered in the Dark Ages. The universe was transparent, but there were no stars yet, just cooling gas.
Dark Ages. Sounds a bit bleak.
It was, until gravity eventually pulled matter together, forming the first stars and galaxies. Their ultraviolet light then reionized the hydrogen gas throughout the universe.
So lighting it up again?
Exactly. And that leads us, eventually, through billions of years of stars forming, galaxies merging, to the present day, where the expansion is accelerating due to dark energy.
That's quite a history lesson squeezed into a few minutes. It's amazing how it went from being so smooth and uniform to, well, the lumpy cosmos we see today, full of structures.
Absolutely. It was that incredibly high temperature and density that prevented atoms from forming for hundreds of thousands of years. Then, gravity, acting on those tiny initial fluctuations in density, slowly pulled matter together, transforming that smooth state into the clustered, lumpy universe we observe now.
So when we look out today, what is the universe actually made of? I know it's not just the stars and galaxies we can see. There's more to it, right?
Oh, much more. According to the Big Bang model and our observations, the stuff we can directly see, baryonic matter made of protons, neutrons, electrons, makes up a surprisingly tiny fraction.
How tiny?
Only about 4 to 5% of the total energy density of the universe.
4 or 5%. That's it.
That's it. Most of the hydrogen and helium were made in the Big Bang. The heavier elements, the stuff planets and, well, we are made of, were forged later inside stars and scattered by supernovae. We really are stardust.
Okay, so 5% is us and everything we see. What's the other 95%? This is where the weird stuff comes in.
This is where the weird stuff comes in. A significant chunk, about 24 to 27%, is dark matter.
Dark matter. The invisible stuff.
Right. It interacts gravitationally. Its gravity was crucial for forming galaxies and clusters, kind of like an invisible scaffold. But it doesn't interact with light or any other electromagnetic radiation, so we can't see it directly.
And we still don't know what it actually is.
Nope. That's one of the biggest mysteries in cosmology. Scientists are exploring various ideas, maybe exotic particles that barely interact with normal matter.
Okay, so invisible scaffolding holding things together. What about the rest? The biggest chunk?
That's dark energy, making up roughly 68 to 71% of the universe.
Even more than dark matter?
Yes, it's the dominant component. And this mysterious form of energy is what's responsible for the accelerating expansion of the universe.
How did it do that?
We don't fully understand its nature either. Maybe it's Einstein's cosmological constant energy density inherent to space itself, or maybe it's some kind of dynamic field that changes over time. Whatever it is, unlike normal matter and dark matter, which pull things together with gravity, dark energy has a kind of repulsive gravitational effect. It pushes things apart.
So it's winning the cosmic tug-of-war against gravity right now.
It seems to be, yes. Pushing galaxies further and further apart at an ever-increasing rate, the fact that most of the universe is made of these things we can't directly see, it really highlights how much we still have to learn. This cosmic tug-of-war is key to understanding the universe's evolution.
It's truly humbling, knowing that ordinary matter is just a tiny sliver of reality. So this naturally brings us to the frontiers. What are the big open questions? What are scientists grappling with right now?
Well, even with all its successes, the Big Bang Theory is still an active area of research. One major area is pinning down the exact value of the Hubble constant, the current expansion rate.
Right.
And strangely, different methods for measuring it are giving slightly different results. This is known as the Hubble tension.
The Hubble tension. What could that mean?
It might suggest there are gaps in our standard cosmological model. Maybe there's some new physics we haven't accounted for, or we need to refine our understanding of the universe's expansion history. And the fact that independent measurements, including from Hubble and now the James Webb Space Telescope, seem to confirm this tension makes it a really compelling puzzle.
So Webb is adding to the mystery there. What else is Webb telling us?
Webb is crucial for peering deeper into the early universe. Its infrared capabilities let us see further back in time, potentially challenging or refining our models of how the very first galaxies formed, giving us new insights into the conditions right after the Big Bang.
And what about experiments here on Earth, like at CERN?
At the Large Hadron Collider, they're recreating the extreme conditions that existed just moments after the Big Bang by smashing particles together at incredible energies.
Wow.
This lets physicists study fundamental particles and forces, including things like quark-gluon plasma, a state of matter thought to exist back then. It's a way to directly test Big Bang predictions and learn about matter's basic building blocks.
And of course, the mysteries of dark matter and dark energy remain huge research drivers.
Absolutely. Figuring out their nature and origin, people are exploring all sorts of theories, even new ideas like a dark Big Bang, a separate origin event for dark matter after the main one.
A dark Big Bang.
Interesting. And scientists are continually analyzing CMB data with ever-increasing precision, looking for more clues about inflation, the distribution of matter back then, and maybe even gravitational waves from the very beginning.
The Hubble tension really does sound like a potential crack in the picture. And Webb confirming it, it feels like we could be on the verge of some major shifts in understanding. What about alternatives to the Big Bang? Are there other credible ideas out there?
Well, while the Big Bang is definitely the dominant model, it's good to remember other theories have been proposed. Historically, and even now, there was the steady state theory.
Right, the idea that the universe was always here, always looked the same.
Exactly. New matter constantly being created to maintain density as it expanded. But observational evidence, especially the discovery of the CMB, really ruled that out pretty decisively.
So steady state is mostly history. What about current alternatives?
There are ideas like eternal inflation, which suggests inflation never stopped everywhere, leading to a multiverse of bubble universes. There are also cyclic universe models like the Big Bounce or ekpyrotic models proposing the universe goes through repeating cycles of expansion and contraction.
Big bounce. So collapse and then another bang.
Sort of, yeah. Some theories also explore modifications to Einstein's general relativity or offer different explanations for redshift. These alternatives often try to address some of the Big Bang's remaining questions, like the initial singularity or the nature of dark matter and energy.
But they don't have the same level of evidence.
Not yet, no. The vast majority of the scientific community favors the Big Bang because of the overwhelming and consistent support from so many independent lines of evidence, the redshift, the CMB, the light elements. But exploring alternatives is part of the scientific process, constantly challenging and refining our understanding. Many of these alternatives try to explain dark matter or dark energy, not as new stuff, but maybe as arising from modified gravity or new dimensions.
Okay, so intriguing ideas, but Big Bang is still the reigning champ, evidence-wise. Finally then, let's look way ahead. What does the Big Bang theory, as we understand it now, suggest about the ultimate fate of our universe? Where's all this expansion lead?
The ultimate fate, according to the model, is deeply tied to that ongoing expansion and the interplay between gravity pulling things together and dark energy pushing them apart.
Right, the cosmic tug of war again.
And based on current evidence, dark energy seems to be winning. The most likely scenario is what's called the Big Freeze, or heat death.
Big freeze. Sounds ominous.
It kind of is. In this scenario, the universe just keeps expanding and cooling indefinitely. Eventually, it gets so cold and spread out that it can't support life or any significant activity. Stars burn out, black holes evaporate over unimaginable timescales. The universe becomes increasingly dark, cold, and empty.
A rather desolate end.
It seems the most probable. There's another, maybe more dramatic, possibility called the Big Rip.
The Big Rip.
This depends on the exact nature of dark energy. If its repulsive force actually gets stronger over time, something called phantom energy, the accelerating expansion could eventually become so powerful it overcomes all other forces. It could tear apart galaxies, stars, planets, even atoms, and eventually the fabric of space-time itself.
Yikes. That sounds unpleasant.
It does. It's considered less certain than the Big Freeze, though, and the Big Crunch. The idea the universe might stop expanding and collapse back in on itself into a singularity.
The opposite of the Big Bang.
Right. That used to be considered a possibility, but the discovery of accelerating expansion driven by dark energy makes it seem very unlikely now.
So no Big Crunch probable. What about those cyclic models, the Big Bounce?
Those models propose cycles, but again, the dominance of dark energy in our current universe strongly suggests the Big Freeze is the most likely long-term outcome. Still, the exact behavior of dark energy remains the key uncertainty, leaving a little wiggle room for other possibilities. It's a good example of science adapting new data on acceleration shifted our view away from the Big Crunch.
The Big Freeze. It's a stark picture. But it's incredible how much we can actually deduce about the universe's whole story from that fiery start to a potential cold end just based on the evidence we've gathered.
It really is. So, to sum up, the Big Bang Theory gives us this robust, incredibly successful framework. It rests on solid pillars: the redshift of distant galaxies, the cosmic microwave background, the abundances of the light elements.
Right.
And while alternative ideas are explored, they just don't have that same breadth and depth of observational support right now. Ongoing research is focused on refining things, particularly tackling the mysteries of dark matter, dark energy, and pinning down parameters like the Hubble constant.
Double tension.
Exactly. And the most likely future, based on everything we see, is continued expansion, leading eventually to that big freeze. It's quite a journey, from Lemaitre's initial visionary idea to today's incredibly detailed, evolving models. It really showcases the power of the scientific method in understanding our cosmos.
A thoughtful pause. So we've seen how that key evidence redshift, the CMB, the light elements, strongly backs the Big Bang. And while other theories exist, the Big Bang model really is the most robust explanation we have based on current evidence. The ongoing hunt for dark matter, dark energy, understanding the Hubble constant, shows our understanding is constantly evolving. Slight change in tone, more reflective. Thinking about this immense sweep of time, billions of years past, and potentially trillions more of expansion. What does that tell us about our own place in this vast cosmos, about the nature of reality itself? That's definitely something worth pondering, isn't it? Something to explore further.